in the years ahead. And as all we know, telecom networks are growing in complexity, in responsiveness, scale, and 6G is coming, and it will be a native. And that means that artificial intelligence will be not considered as a tool, an add-on on the top, but it's a decision maker. In fact, key features for saging networks will be distributed agents at a core, at the edge, at the run, at the user devices, integration of digital twin for real-time simulation and processing, and even every self-fix capability, like self-organizing, self-healing, self-monitoring, self-protection everywhere. And that's really excellent. And also in this plenary section in Restart, we celebrate AI's power to accelerate, to optimize, even to decide. Because artificial intelligence, it will become a decision maker. But I don't have the... Oh, yeah. Thank you very much indeed. And so, but there is also a darker truth with this. That means that when AI is making a decision, it can make like who can get connected fastest, who can get help first, who can get me watched or what else. It can make mistakes, and these mistakes can be unfair or even dangerous. But we have to consider that the dark side of the AI is not where the machines goes wrong, but when the human being stops watching. So the risk is really autonomy without oversight. And but the dark side of the AI is really the space where the human being must shine brighter. That's the key point. And just to better understand what I'm talking about, let's just have a look at the network architecture evolution. The network architecture has evolved from a hardware-defined system where network function are tied to vendor-specific hardware. Then we have software-defined system where network functions were virtualized and developed as software run on general purpose hardware. And now we are increasingly approaching a cloud-native approach where network functions are containerized and orchestrated by Kubernetes, providing flexibility, automation, and scalability. But now a new phase is emerging, is agentic network function, where network function can be considered as an agent, distributed agent, and a distributed agent where every self-organizing capabilities can be delivered, redefined according to agentic AI paradigm. So this is really a new paradigm shift. But this paradigm, there is some risk behind this technology, some risk behind this paradigm shift. And to better understand, let's just have a look at what has been the evolution of AI adoption in telecom network. At the beginning, artificial intelligence in network was mainly related to automation, rule-based automation. If X happens, do Y. Human decided the rules and the machine obeys. Then machine learning came And with a statistical approach, we have the possibility to make traffic forecasting, improving optimization of network, and optimization of maintenance, and what else. Efficiency, we have efficiency, but still passive approach. Now, with agentic AI, a new paradigm appears, and the idea is that the agentic AI start to sense, to act locally, to reason, to decide, and the infrastructure start to be not passive, but it's dealing with decisions. And early version of this agent is already powering some AI native run platform, and even digital twin simulation, and even closed-looped systems. But the problem is that there is a risk, because when AI make decision in telecom network, who can connect first, who can help first, who can be watched, it can make mistakes. So there is a systematic risk when AI agent execute a task. The AI can silently start to reprioritize, and in workflow, AI can bypass some process, and in KPI, it seems as a non-critical, and in policy rule, maybe AI doesn't have the all knowledge representation to interpret the things correctly. And so, for example, in these slides, we can see a city skyline with a sort of almost invisible code algorithm. So there are some areas that are bright, that means connected, and others that are dark, left behind. So this is a sort of a visualization of algorithm inequality. It means that in AI-driven networks, connectivity is not uniform, is data-driven, is dynamic, and we have to be careful that it is non-uniform, can be we cannot transform in unfair in an unfair approach. So behind these slides, there is a deep question. Who decided who get connected to service? A silent algorithm of a human value system? That's the point. So when we have an AI system, for example, we can try to map it into this diagram, for example, where the horizontal has is an ethical gap. It means a sort of accountability parameter that identify the distance between what a system is expected to optimize and what the society, the user, express in terms of fairness and rights. And in the vertical axis, we have the technical risk. Low risk means a system that are stable, predictable, and trustable. And high risk is when the AI is efficient, but with limited accountability and transparency. So we have a sort of, in the left bottom area, is the area where AI really provides benefits with a low risk and a low ethical gap. And in the upper right side, we have blind spot that is technically powerful, really maybe efficient, but ethically fragile. And in this area, we have to ask ourselves, who taking account for this? And So there is a systemic risk that we have to take into account, because when we discuss about AI ethics, typically we, at the moment, take the debate is basically on bias, adversarial attack, and there is a vulnerability. But as we move towards agentic AI, we have to there is a systemic risk, and we cannot stop where the technical glitch start. Let's consider, for example, at a technical layer is essentially where the infrastructure is. I mean, there is, for example, algorithm, model, network component. And at this technical layer, for example, it may happen that AI misclassifies a user as a malicious. But the risk doesn't stop at the technical layer, go upward. And so at the functional layer, where the AI start to executing the task, this misclassification turns in a service interruption, for example. And then we have to move to the organization layer. So, for example, who is the operator aware of what is happening? Is anybody that can override AI or something like that? This is a sort of governance layer. And then we arrive at a human layer where there is the impact on the user. And this is where the risk transforms in an harm. So the idea is that when we move from traditional AI and we approach agentic AI, we cannot consider only the risk, the technical risk. We have to include the harm and even the erosion of fundamental rights. And the idea behind this is that we have to take into account something like a governance by design approach. Let's be honest, when we are in a scientific community, every time that we hear something that recalls from regulation, some enthusiasm tend to vanish a little bit. But what I want to stress is that not only a call for regulation, that it's really important anyway, but we have to find some research direction to take into account of this. And which can be this kind of research direction? It's just, for example, starting to mapping human risk exposure, or develop a prototype that include a rights-aware AI agent, or developing methodologies and tools for including not only technical risk, but also harm, also erosion of fundamental right, and also consider the cascading consequences that will be for that. So it's not only a call for regulation, but it's a call also for research direction. And as a Fondazione Bordoni, we participated both in Restart project, but also in CERIX project. And in CERIX, we start to consider this kind of approach, just a preliminary approach. And for just to take into account not only taking into account how technical risk cascade into human consequences. And for doing this, we constitute a sort of transdisciplinary teams, including 5G expert, system integrator, and cybersecurity, and also legal. Because the idea is that we don't need artificial intelligence, but also collective intelligence. And that's, and in that case, of course, we don't want to address the whole system, because it's an activity that is just right now at the end of the project. But what we are trying to do is try to describe what really matters for doing this, and how can we approach for this. And since we really need a sort of a collective intelligence, just personal, I'm just wondering if there will be some margin maybe in the future also for a collective intelligence among different programs. And just as a closing thought, I would like to say this. In preparing this talk, I came across in a very small but powerful book that is Il Visconte Cibernetico, the Cybernetic Viscount, written by Sideri e Principe, is a Lewis publication. And that was a chance for me to go in and read again some Italo Calvino works, and also appreciate again its relevance also for our time. And in the Cloven Viscount and the Visconte di Mezzano, Italo Calvino imaged the story of a Viscount that is split by a cannon ball in two halves, and these two halves are not really human, and only when they regain the unit, they start to be human. So in the Cloven Viscount, Calvino leave us a warning for our time. So the idea is really stay full. So it's not only sufficient to have efficient and really working system, but also system for human that take it into account. So the warning is really stay full. Stay full, it means in an AI system that takes in account efficiency and harm and erosion of right. And that in less poetical words, it means let's find a balance between overregulation and innovation. Let's find a balance between leveraging AI and mitigating risk. Let's connect dots between disciplines, maybe also between research programs and across system, just to compensate artificial intelligence with collective intelligence and regaining a sort of unit. So thanks to all of you for your attention, and that's all.
Okay, thank you, Marina, for your nice presentation. Are there any questions from the floor? Claudio?
Thanks a lot, Marina, for your wonderful presentation that really opens a very large debate about the use of AI in telecommunications networking. My question is, do you think that the the of the risks that are inherent to the use of AI in networking will limit the applications of AI in particular in safety critical networking, because if there is a trade-off between the cost and benefits. Probably for some applications, the risks are higher than benefits and vice versa. Do you have in mind a picture about which kind of applications cannot use artificial intelligence, or for other they can use?
Yes, you're really perfectly right. This is the point. We have to find a balance between over-regulation and also innovation, because sometimes over-regulation is limiting innovation. But I think that one question that we have to answer every time that we have to do something, can anybody will be hurt? That's the key point. I think that's our human identity. Then we have to make it as efficient as possible, but without losing. So, for example, we are considering like a sort of a digital connected hospital, for example. No, this is a reality. So we can have a sort of a misconfiguration that can introduce some delays or something. We have a lot of systems that can arrange all the things. But sometimes we have some option. For example, we can, for example, limiting the access to a server or making another things. And what we have to decide what to do, we have to take into account the complexity. And yesterday there was also a wonderful presentation by Sergio Barrosa, and the present is really how to have a complete knowledge representation in order to take into account all this issue. This is a research direction, and so we are, most of us are community research, maybe also vendors, you know, and of course when, okay, not for everybody, but sometimes when we have a regulation, we are not so enthusiastic, you know? But what I mean, and that there are research direction to be taken into account to address this issue. Regulation is important, but we need a research direction to take into account. Also to discuss. And for example, just in Iraq, we'll try to develop a semantically rich ontology to take into account of this. But the problem is complicated. We consider a very, very, very simple case. So we have to do a lot of work.
Thank you, Marina. And let us thank the speaker again.
Okay. Thank you.
And let's move forward to our next speaker, Fabrizio Granelli from the University of Trento, who will talk about to twin or not to twin, right? To digital twin or not to digital twin.
Hi, good morning, everyone. So, in this meeting, I think you are probably sick and tired to hear about digital twins, network digital twins. So this will be yet another presentation, but I will start with the story, let's say, so to keep to lighten the mood a little bit. So, you know, this is a mirror. So the mirror was invented by humans 8,000 years ago, with the purpose to understand what the other think about us, because it's a way to perceive how the other people see ourselves. However, some scientists use the mirror as a test to understand the intelligence in animals, for example, because one of the issues is to understand if an animal understands that the image in the mirror is himself or herself, or it's another animal, for example. And what is interesting is that several animals are able to understand that it's their own image that is reflected in the mirror. And the main, let's say, advantage or the main aspect here is not much the intelligence of the animal, but the fact that after a while, animals put in front of a mirror develop self-awareness. So they start to understand, when they start moving, for example, that exactly the image works as themselves. So they develop some sort of self-awareness. They understand that it's their image. So what happens if we put in front of the mirror a network? Of course, if we use a standard mirror, I don't think we get anything very interesting, but let's imagine that in our case, the mirror is the boundary between the real world and the digital world. So what happens if we build a mirror of a network inside the digital world, inside virtual reality, if we want, or inside a computer? This is basically how I believe is the best way to describe what is a digital twin, because the digital twin is not simply a simulator or an emulator of a system, but it is characterized by, of course, the capability to replicate in the virtual world the behavior of the system in an accurate way, but also it is continuously synchronized with the real system. Like when we are in front of the mirror, if I move, my image moves, of course. We all know that. So this happens also in a digital twin. And this is one of the main features that distinguishes a digital twin from a simple, let's say, simulator of emulator, because it is connected in real time. The state of the system is replicated in the digital twin itself. So this holds for any kind of digital twin. So what happens if we think about a network digital twin? The network digital twin can be useful in several scenarios, and I will show you 3 examples and a half, actually, about some applications. But in general, the digital twin can be used for these 4 features. One is to analyze scenarios, so to be able to understand the impact, for example, of actions before requiring to operate on the real network. No telco operator would like that you play with the network just trying to see what happens. Of course, the other thing is networks today are very heterogeneous, so it's difficult to know exactly which will be the effect of some actions, because we don't know exactly how all the parts of the network behave. Another thing is we want to predict what happens in the future. So what is the best way? That knowing exactly what happens in a centralized fashion, but capable of representing the whole. And finally, that connects me to the story, let's say, self-awareness. A lot of algorithms, a lot of solutions like network automation, network optimization, they assume that the network is self-aware because the network has to know what's happening inside it. So there are a lot of applications. Probably you also saw some proof of concepts yesterday, or also today there will be some interesting proof of concept about how to apply network digital twins, especially to network management. That is an aspect that covers a lot of interesting features like detecting anomalies, providing hints to proactive maintenance, enabling forecasting, failure prediction, and so on. So I think that a digital twin can help to develop a lot of interesting scenarios. So let me show you a few examples very quickly. If you are interested, of course, we can discuss in the questions, but also I'm here around. So I don't want to be too much technical, so I don't want to explain you what is this diagram about, but I simplify like this to show you one first example on how to use the digital twin. For example, in this case, it's a project that I'm involved in about security. In security, of course, the fastest you react to a threat, the better it is, but also you have to react in the most appropriate manner. So you must be selecting the best choice among the solutions that you have to mitigate the attack. And in this case, for example, that module that is here you can see this one in purple, is where is the digital twin, because you need to have the capability to emulate your network without playing with the real network so that you can test different assumptions, but also you need to know very well the state of the system, because maybe you want even to predict the fact that an attack is happening in the network or is going to happen in the network. But you also want to have the capability to understand if you select an action to mitigate that attack, whether it will be maybe negative for your users, because sometimes taking an action against an attack can reduce the quality of service. So in this way, you have like a sandbox to play with where you can test. In this case, you is the network itself. So it's not the operator, it's the algorithms that run in the network that will be able to test even many assumptions in parallel to understand, at least in principle, which are the solutions that are most appropriate. Second scenario is, we discuss a lot about sustainability. One of the biggest problems is understanding, in my personal opinion at least, the relationship between energy consumption and the parameters or the KPI that we have as telecom services, for telecom services, because we want data rate, we want high levels of processing, but we don't know exactly what happens if we have, for example, in this case, different kind of virtualization strategies, and we assign one task to a node rather than another. It's very complicated because of the layering that we have, of the side effects that can happen. It's not so straightforward. I mean, we would imagine that it's almost linear. I mean, if we increase the CPU load, for example, the energy consumption increases. That is at all not true because, for example, CPU, they can throttle the clock. So they will change in steps, for example. So sometimes adding something does not increase the energy consumption. Sometimes it's more linear. So who knows? Because when we do, for example, when we optimize the energy consumption in a traditional way, we don't know the specifics of the hardware in most cases. So the digital twin, if it's built, of course, with this purpose, it can have the capability to provide the information also about real-time energy consumption, and it enables, for example, to build even very simple models, like the one that you see here are just 3D charts. But you can see that, for example, if I use virtual machines rather than containers, the pattern of energy consumption is modified. And if I do bare metal, it's even different, and so on. So these differences are very difficult to model in principle. But this is exactly where you need a mirror, because you don't know what is your equipment like. Maybe you changed also from one time to the other. While the digital twin is always, let's say, the most reasonable, let's say, model of your system, because it's continuously fed with real data. So it's actually like a mine full of data that you can use for better knowledge about your system. Another thing is, the third example is the physical layer. For example, you want to know if you fly a drone, which will be the quality of the signal in different places, or you want to study the coverage because you want to, for example, activate some new base stations or things like that. Of course, there are already very well-known softwares that allow to do this, but it's very difficult, even for simulation software that are extremely accurate, to have a precise model of the environment where they operate. And of course, here I'm not saying that we can do better if we don't have sensors, for example, it might be a drone itself or something else that provides also real data to feed your model. So in a lot of situations, the network digital twin allows to have more information and more reliable information, because as I told you, the most important aspect is that you have a continuous communication. Continuous, of course, is, let's say, a little stretch in this discussion, but there is, let's say, synchronization between the physical and real system and the digital version of the system. As I told you, I give you half an example because this is not really a network digital twin, but it can be intended as some, let's say, side usage of the concept, because, for example, you can use the concept of the digital twin to enrich your data. For example, here, there is a very famous data set, I think it's from 2008, something like this, that they recorded in Stanford from imagery from a drone. There is, you see the people on the right. And on the left, there is a 3D reconstruction based on the data. But the difference is that while on the left, we can replicate, of course, in 3D, the system. We can add more users. If we build digital twins that replicate the behavior of the users, we can augment the data. So for people that, for example, are working on segmentation or behavioral analysis, this can help. And also we can change, for example, the way to move the camera so that we can even generate images that are not available. Of course, they are synthetic, so maybe not so, realistic, but this can help to have more data for training artificial intelligence, for example, because in a lot of cases, it's very expensive to build data sets. Or in case of people, there is GDPR and all this stuff. It's very difficult that you can use a video that is available for other purposes. I mean, it's forbidden actually to use it for training AI because you infringe, you go against the privacy. So what's in the future for digital twins? So what are the challenges and which is the future for these technologies? The first thing is, even though I presented you, let's say, examples that are doable today, still there is not much on how to really connect the physical and the digital twin in networks, because the difference between a traditional digital twin and the network digital twin is that in the traditional digital twin, for example, digital twin of a car, it's quite clear which data I need. I need to know, for example, how the tires are moving, which is the status of the tires, or what is the driver doing, if he's pushing the changing brakes and doing things like that. In a network, what is the data that you need to replicate the status of the network? It's still a question mark, because it can be the amount of packets in the buffer of the routers, what the services are generating, what the users are doing, and things like that. So still, there are several works in the literature, but none of them is facing the problem of understanding the impact between the kind of data that you use and what you achieve in terms of accuracy, for example. And the same also for the question when. So when do I need to synchronize? Because I cannot have, of course, a continuous, I did it on purpose before I mentioned real-time connection, but I cannot have a flow of gigabytes of data all the time just to have a replica of my network, because I need another network for connecting the two. So when should I synchronize? How often, or is it based on events or not? These are all open points that still exist. Another thing is, digital twins are becoming very popular, even in networking, and there are already a lot of white papers that in 3GPP, in ETSI, that propose to use network digital twins within the closed loop network management scheme. And of course, this needs standardization, because we need to have standard interfaces to integrate the digital twins. And finally, of course, we can have a single digital twin, that were the examples that I presented, but probably we can unleash the real power of digital twins, networks and not, by networking them together. So there are some scientists, some researchers that already coined the term the Internet of Digital Twins. So, but this is a story that I will teach you maybe another time. So, thank you.
Thank you, Fabrizio. Thank you for being on time. Are there any questions for Fabrizio?
Thank you, Fabrizio, for the presentation. In the end, digital twins for the network are an evolution of monitoring and management control systems that we are used to, right? The impression I have is that, however, is that, in this current trend of research on digital twins, we are missing the goal. With control and management system, it was clear that they were for a specific purpose, which was managing and optimizing the network, right? Apparently, at the moment, most of the research in digital twin is basically identifying the digital twin as the goal itself, not a tool for achieving something else, right? And this has a number of implications. How much detail you want to add in the digital twin. I mean, the detail is not a goal itself. It depends on what you want to achieve, what level of control you want to have. So, you know, in your title, you said not to digital twin. I mean, how far should we go in digitalizing the network, and what is necessary and what is not necessary?
That is exactly the big question about the title. Thanks for catching it. I don't have a definite answer, but of course, I mean, digital twins are for networks are complicated, so they require resources themselves. So I have, of course, agree that they are not the solution for everything, and in a lot of cases, a good simulator can be enough. Let's say. I think that. Probably, of course, one question that is still open, in fact, I mentioned it in the challenges, is to understand exactly which data needs to be provided and what the network digital twin should do. Because, of course, it cannot do everything, because otherwise it's the same network that is replicated yet again. And that is not the purpose, because otherwise you can rebuild it. So, of course, that is not the final goal. Personally, I think that the network digital twins are useful in the cases in which, let's say, we still either don't have, let's say, a definite theory to describe the system. So it's like it can be like a playground to have, you know, at least to have the data in the same place and be able to play also with the history, because it's also can be considered like a movie, the digital twin. So what also you can go back in the past. But I believe that the most interesting application is, for example, the one on power consumption, because it is useful as a way to aggregate data that typically maybe you won't do, most likely. So it's not very common that you have the capability to achieve a given level of detail and, for example, sampling on all the parameters that you want. The digital twin somehow forces you to get that data together and to have it in an ordered way. So rather than saying, I have my sensors that measure the power, I have the system that handles, for example, traffic, the digital twin is already a way to merge that. So I see it more in this direction. So maybe they will help to have a system to get the data together. Then for some application, this will be enough just to get the data. So that is at least what I see myself.
Okay, thank you, Fabrizio. And let's thank you again.
Thank you.
Okay, let's move forward to our third presentation by Federica Battisti from the University of Padova. So this is understanding quality of experience in extended reality from metrics to users. Federica.
So good morning, everyone. Today I'd like to bring in a new perspective, at least different from what we saw so far. And this perspective is the user perspective. And since we're talking about the future of telecommunications, I'd like to focus on a specific application, which is extended reality. So let me start first, for those of you who are not familiar with what extended reality is, to give a short definition. When we're talking about extended reality, as the name itself says, we're talking about something that is not the physical reality that we experience every day, but rather something that is added with extra information. There is a definition from the 90s from Milgrams that basically identifies this extended reality as 3 big classes, where we have augmented, mixed, and virtual reality. The difference is basically the amount of digital objects that are inserted into these alternate worlds. When we're talking about augmented reality, this is something that maybe you have experienced maybe with your own mobile phones. We're talking about systems that still let us see the world, the physical world that is around us, but then we have digital objects that are overimposed. Then we have something more that is mixed reality. And in this case, we have interaction with these digital objects. We can actually play with them, move them around, click them, do any type of interaction. And then we have maybe the type of reality that is most commonly known today, that is augmented reality. And this is the one that is most ready under a technological point of view. And the virtual reality is basically something that projects us into a completely different world. So I know that some of you might be a bit skeptical already, saying, okay, you're talking about things that are not really used or usable today. But there are a lot of studies, and this is just, I picked this website. I don't know if you guys from the top can see it. Maybe the font is a bit small. But there are numbers that are telling us that there will be an exponential improvement in the adoption of these technologies. So the extended reality market, so virtual reality, augmented reality devices, are foreseen to be significantly increasing in the business and in the shipment of devices by 2032. So believe it or not, this is something that we will have to deal with in the coming years. The question that you might ask now is, yes, but where and how can we use this? If yesterday you had a walk in the demo, maybe you bumped into our project space, in which we had a virtual discotheque and then a virtual museum. This is already showing that there are some applications, but maybe something that is most commonly used and also considered as application is the healthcare system. And during the pandemic, there was a big development of techniques for VR, especially for the healthcare sector. And this can be for rehabilitation purposes, for remote monitoring, for training medical doctors. So this field is highly relying on these new technologies. And in the University of Padua, for example, we have a lot of contacts with doctors in the hospital that are asking to work tightly towards new systems that can support also the training. Let's say on a completely different note, there may be shopping. I don't know if you ever tried this website where you can use augmented reality, for example, to fit clothes or accessories. There is a very famous brand of sunglasses. You basically enter your website with your mobile phone or laptop. You just need a camera. Then your face is detected, your eyes are detected, and now computer vision techniques are very well developed. So those sunglasses that you pick are overimposed to your face. You can move around. There's a perfect tracking, and you can actually see how those sunglasses will fit on you. Now, what I want to talk about today is not how well those systems work, because we know that technology is there, especially for VR. For AR, we still have to work a bit more. But I want to focus more on how the user feels, because at the end of the day, who's going to use these technologies is us, the users. So if we don't like it, if we get stressed, if it's uncomfortable, we're not going to adopt these technologies. So first, the thing that we're most familiar with, at least when I studied my engineering in my master's, something that we were taught, it was how to measure QoS, and this is something that we still study today. So we know that there are some requirements for the quality of service for these extended reality systems that need to be respected. So for example, if we have a latency, that has to be smaller than 20 milliseconds. Otherwise, there will be problems, issues, and the user won't feel any more immersed, and their experience will be somehow broken. But we also know that the frame rate has to be pretty high. Typically, even if we can access extended reality using mobile phones again or laptops, the most common way to enter these alternative realities is with goggles. Goggles mean having screens that are very close to our eyes, and this is a big effort for our visual system and brain. So we need, for example, very high frame rate and refresh rate. At the same time, bandwidth is something that is really important in this type of application. If we consider the streaming and real-time interaction with these words, sometimes we might also have 360 environments with high resolution. So you see that there are several requirements. So there is something that we know how to measure beside this quality of service, something that accounts for the user. And this is the traditional way of quality the classical concept of quality that for sure you have found in your career at some point. But when we're talking about quality, like the traditional way is audio-visual quality. So how good a 2D image or a video look when you look at them. So I did a search on the IEEE database. Let's say that the first quality metrics started being developed around the mid-90s. And with these keywords, quality assessment, image quality metric, video quality metrics, you see that the numbers of result is huge. Now, if you're working with multimedia content, you will know that despite this large number, we're always bumping into PSNR and SSIM. Now, let's say more recently, Netflix published this new metric for videos, which is very nice, that is called VMF. But other than that, all the other metrics are not really reliable. So we have PSNR and SSIM that for traditional media can predict the quality that the user will experience. So it looks good, audio and video eventually are well synchronized, and that's it. So something that happened, let's say, from 2008 to 2012, exactly when the first 3D movies started appearing, so Avatar is from 2009, the research community on quality said, okay, these metrics, so quality of service is definitely something that should be there. We know more or less how to measure audiovisual quality, but then we really need to put an accent on the user. So we had to look into a more complex situation. And in 2012, the QualiNet published a white paper with this definition that is very long, so I'm not going to read it, but you can catch the main words that I have highlighted here. So you have delight, annoyance, utility, enjoyment, personality, current state. And all these are related to each and every single user. So the quality of experience is something that aims at measuring somehow those values. When then we moved to extended reality, things got much more complex. And this is because here you have some of the many factors that have to be considered when evaluating the quality of experience for those media. The first is immersion and presence. And that's something that we really want, especially if we're dealing with virtual reality. We want the person to be immersed in the world that they are experiencing and forget about everything else. So the interaction has to be very smooth. The head-mounted display has to be comfortable. Our eyes don't need to get tired. The head-mounted display doesn't have to be so heavy on our head. And most of all, we don't have to experience cyber sickness. I don't know if how many of you tried virtual reality, but sometimes it can cause issues. So this can be eye strain in the simplest case, and then it can lead to nausea, for example, to other people. And plus, there's cognitive load. I don't remember yesterday, someone mentioned about this overload of information that we receive. Well, this is something that has to be well designed in virtual reality, because while, and augmented reality also, because while they're very powerful for conveying information, for teaching people, and for a number of applications, we have to be careful with the number of information that we are delivering. And of course, the ease of interaction. We want it to be very smooth. The last point is social interactions. And this is something that is absolutely crucial, and it's something that has been developed more recently. That is, people want to experience this extended reality together, cooperate together, and not only with virtual meetings in which you sit like an announced Zoom call, for example, but they want to do things physically together. Think about remote support for some activities, or virtual museum when there's a teacher that is leading the student through a museum and letting them, for example, touch statues. And all these are very hard to be modeled. So how can we end up having a model that can tell us how to evaluate those metrics that are extremely dependent by the users? So the first thing that we do, unfortunately, you saw this yesterday in the last talk, is running subjective tests. When you run subjective tests, what you do, you select, for example, in this case, a device, several conditions, and then you have to find a lot of people that will do the test for you. So yesterday we had, in the last talk, there were 400 participants, and the minimum time that I have spent in that experiment was half an hour. Now, you do the math and you see that there's a lot of time, not considering the time it needs for preparing. When we do this subjective test, we can record some things directly. For example, all these headsets, but also nowadays our mobile phones are equipped with gyroscopes, for example, accelerometers that let us catch some information about the movement of the user. But we have an issue there. Besides being extremely time-consuming, we have the problem of not having standards or shared guidelines for running those tests. So for 2D, everything is settled. We have very nice ITU recommendation, BT500, that has been used forever and it works perfectly. It tells us how to do tests. But when it comes to extended reality, we are not there yet. So you can see here from the slide, there are two reference for us that have been published in 2021, 2022. But as you can see, they're only discussing influencing factors. They're not really telling us how to run subjective tests. So there are some other efforts, and as the University of Padua, we're actually part of one of these, which is the second recommendation, that is trying to give some guidelines. Both of them have been submitted to ITU, so we still don't have them, we cannot use them. But definitely there's a lot of work towards this. But again, now if we define these models, we will know how to run subjective tests, most importantly, how to process this data that are collected. But then there are still some things that we miss. So all the things I've mentioned earlier, the comfort, the interaction, the ease of interaction, how can we measure that? Well, unfortunately, till now, the easiest thing that we can do is to have questionnaires. Surprisingly, those questionnaires are quite old. They've been developed in the 70s, 80s, and for other purposes, but then they've been readapted to be used for virtual and extended reality. The first one that is the most commonly used is the simulation sickness questionnaire. Simulation sickness is basically a questionnaire with 16 types of discomfort, like, again, high strain, headache, and then you ask the subjects of the test, how did you feel about that? Have you experienced any of this discomfort? And so on for all the other options. And you imagine that we have to select carefully the questions that we ask, because we cannot, of course, have people there sitting and asking questionnaires for hours. So you have another example there that is quality of interaction, social presence, and if you want any reference, I can give you after the talk. So where are we now? We are in the phase of still trying to understand those technologies because they are evolving very, very quickly under an hardware point of view, software point of view. So we are trying to catch up with all these developments, and especially, and something you saw it already yesterday, there are new and new senses that are going to be included in this experience. So for the moment, we basically rely on vision and audio, which is something that we know well how to model. But then you have touch. So yesterday we discussed about that, and also in the demo that we have for our project, there's an example of an experience that includes touch. So you will have gloves, and you can interact using gloves. You can have smell. Let's say that with taste is a bit tough. The only thing I saw is a person trying to lick a screen, which is not like the best thing that I would like to have. So for sure, we know that things are changing rapidly, so we have to adapt and try to figure out how to implement this. And then this is something that also Marina said, so let's stay whole. We need to act as a cross-disciplinary team. For sure, psychologists are a group of people that are always been on board when talking about quality. I've always worked in tight interaction with them. But of course, and this is something that also in Padova we are discussing quite a lot, there's a moment in which the network side and the multimedia side have to work together, because if we want these technologies to really work, we have to try to figure out how to match together quality of experience and quality of service in an efficient way. Then, of course, we have to have use cases in which people will actually use those technologies, which is something that is actually developing pretty fast. And also diversity and inclusion have to be there, because there's a lot of people that have troubles in using these devices. So we have to understand how to handle those cases to make it accessible to everyone. And last one, which I put it as a last item, but it's a big, topic, is ethics, and especially security issues. Again, in Padova, we are working on the re-identification of people using head-mounted display. So our first results show that, for example, if you have enough traffic to analyze, you can discriminate between users that are, for example, playing a game. So this poses some challenges that definitely have to be addressed. Thank you.
Thank you, Federica. I have a question myself. What about objective quality assessment? Because you elaborated quite a bit about subjective tests.
Yes.
Maybe some words, if possible.
Yes, this is actually the final goal, because we don't really want to get to subjective tests every time we have something. So there have been some studies, but it's very hard for the moment to do that. So in some cases, there's also been a trial to go from a subjective test, collecting a lot of subjective tests, and then use AI approaches that unfortunately didn't work. So far, we are very far from a model, but that's the let's say
final goal.
Yeah, definitely.
Okay. Thank you, Federica.
Thank you very much also for the details for the KPI for the standardization body. And according to the standardization body, in particular the European BEREC defined the characteristic of a very high capacity network. I believe that parameters are not suitable for this kind of services. So do you believe that is it necessary to consider a new specification for networks? I believe so.
What is happening on our side, let's say on the multimedia side, definitely we're trying to see how to deliver a specific level quality, while decreasing all those requirements. For example, one among all is compression that can be selective. So in VR, for example, you have a 360 content. And so if you're able to stream only with high resolution the portions that are actually the next that you're going to visit, this is something that can be relevant. And actually part of Restart project, which we are working on, refers to this. And so this is definitely something. And then I think we discussed yesterday with Antonio during dinner, there was this idea of quality. It's not that quality is we always need higher and higher level of quality. Like, do we really need 4K or 8K? Maybe full HD is completely fine. So it's also trying to understand where's the limit, where's really the quality that is enough. So maybe those numbers that are actually much larger for the ITU recommendation, if I remember correctly, for high level 4K immersivity, it was there was a requirement up to 5 gigabit per second, which is kind of a lot. So definitely, I think those are, we will shrink these requirements, but there's a lot of research going on that. Yeah.
Okay, thank you again, Federica, from all of us. And let's move forward. We have Ernesto Ciaramella from Scuola Superiore Sant'Anna. And his talk is entitled High-Speed Wireless Communications for Satellite Nodes. Okay. Ernesto.
Okay, thank you. Good morning to everybody. We are going to talk about real hardware now. And I will spend, I would first spend a few words by recalling what are satellites. Everybody is assumed to know, but just to recall that those are autonomous vehicles that are orbiting around Earth. Various different type of orbits are feasible, and probably the most popular till a few years ago was a geostationary orbit, where the satellite looks stationary. But today, we are all familiar with low Earth orbit, LEO satellites that are traveling at much lower altitude, kind of 500 kilometers. Why do we use satellites? We use satellites a lot. We use satellites for navigation, for monitoring, pollution, commercial route, emergencies, strategic targets. And we also use the satellites for communications. So it's worth recalling that around 1% of long distance data is carried by satellite networks. Here you see a picture of satellites in low Earth orbit. And I should not possibly not even talk to you about that, because everybody knows that today we are talking about this issue mostly because of Starlink by SpaceX, which has deployed a huge constellation which is providing services almost in every country in the world. And this is also a picture that you should be familiar with. There are also other relevant players such as Eutelsat, Iris, in the future Iris Square, and so on, but I would say that Starlink by far is the first one today. Let me spend a few words to recall one key point that is frequently misunderstood. Sometimes we hear we will use satellites if transoceanic cables have a problem. This is technically a mistake, a huge mistake, because the capacity that you can carry out with satellites is several order of magnitudes below those of transoceanic cables. If it happens to you to speak to military or politician, please convey the message, because they don't know. Okay? Transoceanic cables for the student is able to carry, the newest one is 200 terabit per second, okay? And this is gigabit if you are good at doing that. So there are also strategic activities about satellites. As far as we know, there is no operating weapon in the sky, but we know that many nations have orbital surveillance network to observe the possible harmful activity of other nations. You can see, if you comment, you know that North Korea was interested to buy satellites, and they are not using for communication, strictly speaking. But also another important technological development is hyperspectral monitoring, which is used for a lot of application, both civilian and non-civilian application. All those applications need data, because you collect a lot of data in the sky, you have to bring this data down, okay, which asks for telecommunication. Just another last slide about satellites. This is a picture recalling the number of satellites in orbit in the last 40 years. This is a logarithmic axis in Y scale, as you notice, and it's impressive. And again, we expect an increase of a factor of 14 in the next decade. in the data volumes that is generated by those satellites. So this is just to conclude that if you want to be ready for the future, you must have high-speed transmission from the satellites and among satellites. And now we come to communication. First of all, you need high frequency. You know, if you want to transmit fast, you need high frequency. But also there is a problem related to electromagnetic propagation. Electromagnetic waves tend to spread, and they spread faster if you increase the frequency, if you decrease the frequency. So here is a picture I redid from NASA. This is the Earth. And what you see in red, I don't know if there is a pointer here. Yeah, this is the red circle, is the illumination area that you get if you have 1 meter antenna transmitting from the moon using radio frequency. In the center of this circle, you can notice a green dot. That is the illumination circle if you transmit using infrared light. So you understand that if you reduce the intensity, you reduce signal-to-noise ratio, you reduce bit rate. If you want to go fast, you should use the green area. The big issue that you can, of course, understand from this picture, you need the very, very high accuracy in pointing. Because if you miss Naples and you target Sicily, you're lost. By the way, this is a huge problem for deep space, but that's another story. So the key point is you want to transmit fast, you must move to high frequencies. And the first option, you increase the frequency from 2.8 to 7 to 77 gigahertz, and you have much more bandwidth, and you can transmit faster and faster. The expert of this is Claudio Sacchi, who provided kindly this slide. And this is the first research trajectory you have. You have various families of extremely high frequency that you can use for space communication. And they have several benefits. They have high directivity. If you increase the frequency, you can have a smaller antenna. You can have higher antenna gains and reduced size of satellites and speed up to 50 gigabit per second. Unfortunately, there are other issues. That is, you need accurate pointing, propagation losses. You need the specific hardware, and this is a point. When we talk about this, you need hardware technology. You must have a new solid-state amplifier, and this is sensitive to rain and fog. This is not just paper. There are examples of experimental realization, which are cited here, again, thanks to Claudio, who provided these images from Aldo Paraboni and a CubeSat. This is a CubeSat, a small satellite made of cube units that are 10 centimeters wide. And now I would like to take a step back. Sorry. Oh, this is a step back to 15 years ago, where in Sant'Anna we demonstrated this for the first time, a huge capacity WDM free space optical signal system. WDM is wavelength division multiplexing to the students. Means you have many channels with different colors, all transmitted together through the same channel. And this was done outdoor, 200 kilometers back and forth in Sant'Anna. And it was the first demonstration that you can have a WDM transmission in free space. But also, what you see in the green area is that most of this was realized building upon components that were commercially available for fiber transmission, which, by the way, are the result of 50 years of R&D. So the key part here is the optical part. This is the key novelty in this experimental demonstration. 15 years ago, people are thinking about using, and they're actually using, this concept to realize free space communication in the infrared region using optical wireless. Again, the key benefit is that you use devices that you have already available. So you don't need to develop new technology. And of course, if you use optical waves, you have the highest directivity. You have, in principle, very small antennas, and you can have a huge speed. The previous demonstration was 1 terabit per second, but on a single channel, you can easily reach now 100 gigabit, and you can scale up by multiplying the number of channels. Of course, you have problems. Thanks to Murphy law, you need also very, very accurate pointing, much more than for EHF. Also, infrared signals suffer from very small perturbation in the refractive index of the air and turbulence effect. This is well known to our colleagues from electromagnetic waves. It's propagation through inhomogeneous medium, and it gives a lot of unpleasant effects. Of course, infrared is also sensitive to rain and fog, and you need some also new hardware, such as new telescope and adaptive optics. I'm not spending time on this because it's very complex. It's taken from astronomy, but it's moved to communications, and unfortunately, you need to work a lot to make it work for communication as well. So the vision that is considered is a vision like this for free space optics. Links from the Earth to a satellite, from a satellite to the Earth, and also optical intersatellite links. And not to mention deep space, this is to the moon. You may say, okay, very nice. It could never work. It works. It worked. 2 years ago, this was announced by SpaceX. It was the first demonstration of laser data communication through satellites. NASA has developed in the last few years T-BIRD, which is a project to transmit data at 200 gigabit per second down the Earth using a laser, actually 2 lasers, it's WDM. Starlink announced they are using optical intersatellite links at 100 gigabit per second using 3 terminals on each satellite. And finally, China, because of course you cannot leave China alone. They just announced that they have demonstrated 100 gigabit from satellite down to Earth. And now let's come to restart. Within ETA and TN project, we have developed a unified approach to compare the different technologies and to see in specific cases what are the benefits and issues of the different technologies. This is a picture of the network. Of course, you have a lot of links. We have just isolated some of those that we think are the most relevant, which you can see in red. That is basically transmission from the ground to the node, either in uplink or downlink, depending on technology. We choose what was the worst case. And we also fixed a short-term objective, which is 2 gigabit per second transmission for all the nodes. That is the UPS, the LEO, and the GEO. And a long-term objective, which is 100 gigabit per second transmission for UPS and LEO, and 10 gigabit for GEO. Of course, now I'm not going to explain you the methodology. I'm not going to give you the equation. I'm not going to give you all the figures. I'm just giving you the results. This has taken the work of 20 people, summarized here. Here you see the most relevant link parameters for EHF and free space optics. And you can see in green what are the parameters we like, in orange what we don't like, and in red what is the most problematic issue. So the diameter is in general of the antenna is in general much smaller for free space optics than for EHF. And this is a key benefit if you think especially about the small satellite. NASA is using CubeSat to do this. Pointing error, that is accuracy in pointing, is an issue. Especially for free space optics, you need a very high accuracy, and this is an area where we have to work a lot. But this seems to be feasible with an effort. Also, range of transmitted power seems to be feasible in most cases, but for geosatellites, where we need very high power amplifiers that are presently under development. There are initiatives, so we think in few years, for geosatellites, this 47 dBm would be feasible. What is mostly relevant is that for long-term objective, we see that the 100 gigabit at present is not feasible with extremely high frequencies, which are limited to around 50 gigabit per second due to bandwidth constraints and regulations. This is feasible with free space optics, and for geosatellite, this is feasible with both technologies. Again, you may say, okay, you have done everything, we can stop. We can now start working on the software. No. There is a lot of real hardware to do. There are some missing devices and technologies, especially about the pointing, the telescopes, the antenna, and so on. Some of the technologies may be tested on ground. They work, they can have issues when you put on a flying satellite, especially dealing with acceleration, temperature, radiation. Whenever you have these hardware put in operation, I speak especially about free space optics, you will always, according to the theory, experience some flat fading effects. And devices are not designed, the transceivers are not designed for that, because they are designed for a network which is binary. It either works or stops working. So this is a huge problem. And finally, you also have network issues, such as if you have flat fading, if you see issues about turbulence, rain, whatever, you must develop strategies for rerouting, protection, retransmission, and so on. So there is a lot of work to do yet, but I'm quite confident it will be done. Okay, with that, I want to gratefully acknowledge all the partners of WP3 in ITA and TN, which have all contributed to this work. And I thank you for your kind attention.
Thank you, Ernesto, for this very nice picture you provided us with. Any question from the floor? Okay.
Thank you, Ernesto. So I have a simple question. You know, in wireless, we test over the air, okay? But, you know, how can you test free space optics when you started talking about hardware? So how can you test in research the free space optics that you plan to do between satellite and ground. So how can you test it? I understand all the pointing, blah, 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 but you know, I design a method, I design something, I want to test it.
Yeah, okay. It's a very nice question. I did not spend much on this. I hope I can give you a satisfactory answer now, otherwise we talk later. You can test free space optics on the ground in terrestrial link, and this has been done. I have shown something. But if you really want to test free space optics from satellites to satellites, you have to go to NASA or you have to go to China, because those are people who are really testing these devices in the space. T-Bird was the first project led by NASA, JPL, and MIT. They realized the CubeSat. It's a 3U CubeSat. I'm not sure if you are familiar with CubeSat. It's basically 30 centimeters times 10 centimeters times 10 centimeters with transceivers, and they have tested downlink. I agree, it's a mess, because the big problem is the channel. Our colleagues from Campi Elettromagnetici would be enthusiastic about that, because there is a lot of work to do on the channels, but it's very difficult to make experiments. So most of the channel is guessed using theory, simulation, and so on, but to really make a verification, it's hard. This is why, for instance, Starlink is already using optical inter-satellite links, because it's very complex, because satellites are traveling at kilometers per second. So pointing, it's not simple, but it's still under control because you are out of the atmosphere. The key point here is atmosphere. All the effects of light propagation through atmosphere have been investigated by models, but there are very limited experimental tests. So you have to try and guess. T-Bird started 2 years ago. The first test reported an average of 40 gigabit per second downlink speed. After 2 years, now they are at 200 gigabit per second. They did not change the hardware. They just changed the pointing strategy, the accuracy of some specific elements. So this is a point. And still, downlink is the easiest part of the game, because uplink, you have a kind of leverage effect. Passing through atmosphere, the beam suffers from deviations and then moves. So it's different if you go down and you have this effect at the end of the path, than if you are traveling uplink. So I'm quite confident that in some time, maybe in 2 or 3 years, we will see anyway this. The big problem is that this is carried out by private companies. We will never know how they are doing.
Okay, thank you, Ernesto. Let us thank him again. So, last but not least, Roberto Verdone from the University of Bologna. Will 6G be able to address the requirements of future industry use cases and generate, let me see, scalable business?
Okay, thank you. Okay. So the question is, will 6G really be able to do what 5G promised and didn't do? I will offer you my maybe unexpected and multidisciplinary answer or vision to this question. serving the industrial network, serving the Industry 4.0. This is what 5G promised and didn't do, and this is what 6G should be able to. Look at me. What is my future? Is it in front of me or is it in my back? Front or back? What is my future? What do you think? Front or back? Please, I want to hear your voice. Everyone agrees front, right? Everyone agrees that future is in front of us because we belong to the Western culture. But you know, there are many cultures in the world where people would simply say, of course it's in your back. And the reason is, if you listen to their statements, that they say, come on, future, you don't know future. You don't see future. You cannot touch future because it is unknown. So of course, what is unknown is in your back. On the opposite past, you know it, you can handle it, you see it, so it's in your front. Makes sense, right? But still, everyone here agreed on the fact, because we have this common viewpoint, that future is in front of us. It's a Western culture thing. So what the lesson learned here is that even when something appears so obvious to you, to your community, maybe another community might think totally different. Now, the actual topic of my speech today is the connection between this community, the telco community, and the community of managers of industrial automation companies. Those we would like them to buy our 5G and in the future our 6G. This is the topic, how we do communicate. There's a problem of communication between us and them, between these two communities. And that's, to me, one of the main reasons why we didn't sell 5G to the world of industry. So I've been working in the field of industrial networks since 10 years now, and I've been talking to many managers of big companies or medium companies in the field of industrial automation. I can tell you that there's a communication problem. Actually, for those of you who were active in this field in the first 5 years of this segment here, when 5G was standardized, we heard many times sentences like, oh, 5G will be the enabler of the fourth industrial revolution. The automation industry will be revolutionized by 5G. But then, a lot of disillusionment, of course, a lot of disappointment, because this didn't happen. 5G is a failure from this viewpoint. It's totally a failure. So the question here is why it was a failure. But the most important question is, what should we do now that the standardization of 6G started a couple of months ago in order to avoid failing again? These are the two questions that I will address today. So let me start from the why. I can tell you that the unsuccessful story of 5G in the industrial automation world was predicted 40 years ago by a man, yes? This gentleman here, Daniel Kahneman, a psychologist who got the Nobel Prize in economy like 20 years ago, that for 50 years studied psychology and the science of behavior and communication. And it's actually him that told, no, 5G will be unsuccessful 40 years ago when talking to the C-levels, to the executives of the industries. In fact, there's a number of stories that I can tell you about the theories of Daniel Kahneman. And the first one I will start with is this one. When it's time to predict, real experts, and I see many real experts here, are always wrong. This is it seems a simple and stupid statement, but actually there's a lot of theory behind this. We are always wrong when we predict what a new technology will be about. That's a great problem, of course, for all of us. But there's an even more important problem that we suffer from, that I will tell you in the next 2 minutes. First of all, Daniel Kahneman is very well known, and this is one of the reasons why, together with the prospect theory and so on and so forth, why he got the Nobel Prize, for his theory of two systems. Basically, his model of our central nervous system is based on just two systems, System 1 and System 2, as he calls them. System 1 is the instinctual part of our brain, which is basically here. And System 1 is the one that always reacts to stimuli fast. It uses associations. Oh, there's a stimulus, and I associate to this a reaction. It's fast and inaccurate. On the opposite, system 2, which is more or less here in our neocortex, system 2 is the rational part of our brain. It always comes after system 1. It always comes later because it's based on the different types of neural networks. But the key point is that sometimes it simply doesn't pop up. There are many people in the world that simply don't use their system 2, and they always take decisions and react to stimuli based on system 1, on the instinctual part. Now, based on this model on the two systems, Daniel Kahneman said the entire population in the world can be split into two categories. Humans are those who are dominated by system 1, and, well, he called them econs, short name for economists, those who are dominated by system 2. I prefer to call them NGs because this model can be applied to us perfectly. NG is a short name for engineers. So the point is that what he said, the people is split in two. The entire world population can be split in two, humans and NGs. And actually, the majority of people are humans. So we are the minority, I can tell you. And when I say we are the minority, that's because, well, in my studies, because I'm applying his studies to my own activity on soft skills, first I realized that there's a gray zone of people who are not perfect, NGs, not perfect humans. I call them unconsciously skilled, but still, despite this gray area, it's true that most people are humans, not NGs. In my courses on soft skills in business schools at the university, I'm used to take simple tests in 5 minutes to measure whether people are humans or NGs. But I don't need to take any test here. I'm pretty sure that there are no humans in this room. I'm pretty sure. And this is our problem. This is our problem. Yes, because on the opposite, according to Daniel Kahneman, all C-levels of companies are humans. Good managers are humans. NGs are not good managers. So if you talk to a CEO that takes 10 decisions per day, he has to react fast to things. He doesn't use the system 2, his system 2. CEOs are humans. So now you see the problem. Last statement from Daniel Kahneman. NGs and humans can hardly communicate. So we, NGs, prepare for them 5G, which is a wonderful technology, and they didn't buy it simply because we didn't communicate to these people properly. Because they are humans, we are NGs, and humans and NGs. Well, for any of you engineers here, having maybe at home a wife or a husband, which is system 1, you know what I'm talking about, right? Okay, I see some faces. So the point is, we need to find a way to communicate to these people properly, not as NGs, but acting as humans if we want to convince them to buy our technology, 5G today, tomorrow 6G. So it's a matter of communication. And now we'll try to go more technically into the discussion of how this bad communication we had with them had a consequence in the past years, I believe in the next 5 years as well. But what we have to do is to do better in the next decade when 6G will come. So 5G, a lot of disappointment from our side because we didn't sell it, from their side as well, because they were expecting something from 5G that didn't come. This disappointment is not a technical fact. I mean, I know that some people can say, oh, but motion control over industrial machines requires a latency of 0.1 millisecond, and 5G still can't give it because it gives roughly 1 or few milliseconds. But that's not an issue. There are plenty of applications in industry factories where you can live with 10, 15, 20 milliseconds. So that's not an issue. And even the reliability of 5G is still 3 nines. They expect 5 or 7 nines. That's not true. That's only for some specific applications. But there's plenty of use cases in their industry plants, in their industry processes, where 5G might be offering the proper requirements. So it's not a technical issue. It's a question. It's a matter of bad communication between our community and their community. Examples. First, we made 5G totally unflexible. I know that 5G is URLC, but URLC is too complex, it will never come. MMTC, we made 5G like this, but if you really talk to them, you will realize that there are hundreds of different use cases in the world of industry automation, and they want one solution for all of them. So you cannot go with 5G, which is like a cannon when you have to shoot a small insect. You need to have something simpler, low cost, low complexity, which is not 5G. 5G promised too much, so this is something that in communication is always a problem. When you promise you will offer something and then you don't, URLC, which didn't come and will not come. And then there's a lot of perception of distrust. They don't trust in 5G. They believe that 5G is, it's easy to steal data from 5G. No, the real story, we know it, but it's possibly easy to steal data from the cloud, not from a wireless link like 5G is. So basically, there's also a perception of distrust, which is something which comes from bad communication. Moreover, we promised 5G will be for industry automation, but they clearly state, hey, you didn't do anything to try really to match your technology to our needs. We have a number of industry standards, just to mention one, TSN, which are essential to us, but you didn't take care of them. So another problem, which is basically of bad communication. And finally, there's a lot of schizophrenia in our community. We have a new release, a new technology every 18 months, right? While they build a system in their factories and they keep it for 15, 20 years. So you cannot approach them saying, oh, but there will be a new release in 2 years from now. It doesn't work. It simply doesn't work. Bad communication. So now let me come to the what. What can we do in order to avoid being unsuccessful again next year, when we will start actually going into the standardization phase of 6G, and we will make 6G with the clear intention to serve the Industry 4.0 and the industrial automation world. We have to avoid the mistakes we did earlier. So take this part, especially for the students here, as research hints, if you want. First, I believe that given this huge heterogeneity of requirements, of use cases that the industry world offers, they need a solution which is really scalable, which means something that can scale down to a very simple, low cost and low complexity solution. So we need both a cannon and a sling at the same time. There's a number of options. One is, for instance, to standardize a dual radio, not a single radio, a dual radio. Of course, from the physical layer, I know that multi-carrier is very flexible, of course. But what about the protocols? They are not in 5G. They're not flexible. So, for instance, think of random access together with scheduled access, which have two different types of behavior with respect to complexity and so on and so forth. Or a scalable PHY. Invent a scalable PHY and a scalable set of protocols on top of it, which can really scale down as long as it is needed by the application. According to the goal, the real goal of the application, the real need of the application. We definitely need to standardize 6G so that it will be compatible to the industry standards, including TSN, which means jitter zero. Not only zero latency, jitter zero, reduce the distribution of latency, which is an essential fact. Today, we are offering very low latencies with a standard deviation of 6 milliseconds. Less schizophrenia. Let's try to standardize something which we know will be stable for a long time. Otherwise, they will not buy it. Focus on the real needs of industrial applications. And this to me means get out of the lab, go to the factories, talk to them, look at how they work, look at the industry processes, the industry factory floors, because it's only when you are there that you realize what are the real needs. It's not reading the 5G ACA white papers, to be honest. And finally, goal-oriented communications, communications which are really targeted at the use cases, which was not the case for 5G. So when I say get out of the lab, this is what we try to do in our Restart project, S9, the structural project number 9 at the University of Bologna, which is dedicated industrial networks. We had 1 week ago a very nice first workshop in Lecce where we went to visit 4 different companies, and we realized what are their real needs, their real use cases on the factory floor. And I can tell you that we are going to organize on November 11 another workshop of the same type. We intend to have visits to industries, automation industries companies, so you're all invited to meet us. And finally, let me conclude with the first steps that 6G took in the past few months. That 3GPP took in the last few months. The standardization of 6G started actually in March, and the first important document which is going to be delivered is this document here, which describes the use cases of 6G from a very high-level perspective. I got it from the friends from FiberCop, thank you very much. I just counted tonight the number of use cases that are described. It's more than 120, which means that 6G is about everything, which I don't like, to be honest, because when you say that something is for everything, like it was for 5G, it's going to be a failure. So we should really focus on what is the use case we want to address with 6G. This is for those who work in the standardization. Let me conclude by inviting you to follow us with this initiative that we started recently, which is supported by Restart. It's an initiative, Orizzonte 6G, that we have put together. You see the companies which are involved in the initiative, and the scope of this initiative is to follow the 3GPP process of standardization of 6G to realize whether we are going in the right direction, and to tell companies, because it's dedicated to Italian companies, in order to tell them what is going to happen in the next decade. We are organizing an event which will be actually the 3rd day of the GTTI annual event that is going to happen in Bologna, 15 to 17, and on the 17 in particular, we are organizing this workshop where you see the people who's going to talk, where we're going to talk about what are the first steps taken by 3GPP in the direction of 6G, discussing how we, as a nation, would like 6G to be, so that we will not repeat the unsuccessful story of 5G, and hopefully will make a better 6G. 6G is a new opportunity for all of us. Let's follow the standardization process in order to anticipate the steps, and let's try with our research, we are researchers, to push the standardization in the direction of something which is more successful than 6G. Thank you very much.
Thank you, Roberto, for your bright talk as usual. Are there any questions for him from the floor?
Claudio.
More than a question, I have a comment that might complement your presentation. In the historical evolution of the mobile communications from the 1st generation to the 4th generation, we had a straight line. The straight line from 1G to 4G was substantially the increase of capacity and the availability of new services put in your hands. Then in 5G, they decided reasonably that the race was end, and they designed the idea of the Huawei's hypercube. Do you remember? So probably we lost inside the hypercube, because the hypercube is a too complex and NG conceived structure where there is everything. There is the sector of the mobile communication, the sector of the virtual reality, of the augmented reality. There is also the corner of the industrial communication, because there is, but probably the communication was lost together with the orientation inside the hypercube. I think that in the 6G, an effort of making things clearer and more oriented to the specific application target should be done, but without losing the visionary attitude of 5G, simply avoiding to lose ourselves inside the hypercube. This is my comment.
As you said, it's a comment on other questions, so I don't have to reply, actually. I just add that I hope that 6G will not try to be revolutionary, but an evolution of 5G, because 5G is a good technology, except that it is not flexible. So we have to find this flexibility in 6G that was not available in 5G. Okay, thank you.
Thank you, Roberto, again, from all of us.
Thank you also, Maria Luisa. So we saved some minutes before the break for thanking our sponsors, All Be Smart and Measure It, and we will give them the floor for a couple of short presentations. So please. Want to use this?
No, I can stay here. Okay. Good morning, everybody. My name is Fabio Signorini. I work for Measure It. I know that in a few minutes there will be the coffee break, so let me permit to switch in Italian, so I will be a little bit more effective. Grazie mille ovviamente per questa opportunità. Da qualche anno siamo sponsor di questa manifestazione. Anche oggi siamo qua con dei nostri partner, All Be Smart e NTM Tech. Measure It è una società italiana presente sul territorio italiano, ma non solo. Siamo in primis i distributori di National Instruments e suppongo che molti di voi già conoscano e stiano anche utilizzando le radio di Etus che sono state realizzate da National Instruments. All Be Smart è una società portoghese, abbiamo qua in sala Clara Aidos, nostra collega, la quale rappresenta All Be Smart. All Be Smart è, come vi dicevo, una società portoghese che lavora a stretto contatto con il consorzio Open Air Interface e negli ultimi 10 anni si sono differenziati e hanno sviluppato questa piattaforma chiamata OI Box. OI Box è una piattaforma trademark, quindi unica nel suo genere, ed è una piattaforma che nasce proprio per testare, simulare e sviluppare le reti 5G e 6G. Nel portfolio, nel catalogo di All Be Smart potete vedere che abbiamo diverse soluzioni che partono dal mondo FR1, la prima che vedete a sinistra si chiama WaveBox 40, integra direttamente una radio. Il passaggio successivo è invece l'OIB Max versione Max, la quale rimane sempre come FR1, ma ha la possibilità di poter utilizzare delle radio che sono state precedentemente o comunque acquistabili dall'utente. L'evoluzione di questa piattaforma va verso il supporto ai nuovi range FR2 ed FR3 fino ad arrivare ad una soluzione quindi completa della proposta All Be Smart. Diciamo che il parametro di differenziazione di All Be Smart è proprio grazie a questo dashboard che permette di controllare in tempo reale i componenti della rete, così come di poter visualizzare delle metriche di throughput, di latenza e di qualità del segnale. Grazie alla collaborazione con TMTech, abbiamo qua oggi Vincent Lee, siamo in grado di entrare nel mondo dei millimeter wave. In primis volevo parlarvi del kit didattico che abbiamo tra le altre cose anche nel desk in sala presentazioni. TMTech ha un catalogo veramente molto ampio, come dicevo, nell'ambito dei sistemi millimetrici. In particolare realizza una serie di prodotti che permettono di estendere l'utilizzo delle software defined radio in ambito millimetrico con questi mixer up and down converter che nella fattispecie sono in grado di arrivare fino a range da 24 a 44 GHz. Una nota di merito sono le frequenze intermedie perché, come potete vedere, queste mixer hanno la possibilità di essere utilizzati anche con qualunque tipo di vector network analyzer e generator in commercio. Nel centro di questa pagina, di questa slide, poi potete vedere i beamformer, sempre di TMTech, quindi delle antenne che sono in grado di poter operare sia in vari range di frequenze e sono disponibili anche in modalità a 16 canali oppure a 4 canali. Tutte queste lavorano tipicamente in half duplex. Ce l'abbiamo qua, crediamo probabilmente siamo anche gli unici ad avere in questo momento una soluzione X-Rifle dinamica. Sono disponibili due sistemi che sono in grado di lavorare con un unico controller ma in range di frequenze diverse, quindi sono in grado di supportare sia il 5G millimetrico che il 5G di precedente generazione. La caratteristica di questa antenna, del controller in particolare, è quella di poter collegare fino a 4 X-Rifle contemporaneamente. L'invito sostanzialmente, ho praticamente finito, è quello di venire a trovarci nell'area demo. Abbiamo questo setup completo, quindi saremmo veramente molto onorati se riusciste a passare a spendere qualche minuto per vedere e toccare con mano questa tecnologia. Io ho finito, vi volevo ringraziare ovviamente di questa opportunità nuovamente.
Grazie Fabio, grazie.
Grazie Antonio.
Abbiamo l'altra presentazione o solo voi? O la tua? No, finito. Ok. Domande? Io volevo veramente ringraziare per il supporto che ci ha dato anche in questa occasione e credo che la compenetrazione, no, di esperienze fatte nei nostri laboratori con le attività, con questo tipo di aziende è importante perché di fatto la spinta sperimentale che abbiamo avuto è dipesa anche dalla disponibilità di questo tipo di soluzioni. Grazie mille, vorrei ricordare che adesso c'è il coffee break e poi riprendiamo alle 11:35. Anticipo di 4 minuti. Welcome back. We are ready to start the next session, which is dedicated to a set of live demos, and the session will be chaired by Michela Meo. Michela, please.
Grazie. So good morning again. Welcome to this session dedicated to demos. So the first one will be presented by Francesca Cuomo and Marco Casalbore from the University of La Sapienza in Rome. So please.
Okay, thank you, Michela, and welcome back after the coffee break. So the presentation of today is given by myself and Marco Casalbore, who is a PhD student in Sapienza, and we're going to present the proof of concept of our focused project, WITS, Watering IoT, and the Sprint, that is a Cascade project. The main partners in this project are University of Rome La Sapienza, University of Palermo, and Unidata SPA. So the topic, the goal of our proof of concept, that is named Splash, is to derive a smart platform for large-scale holistic water management. Holistic because we integrate in this unique platform simulations, IoT, and machine learning. The final goal is to develop a framework to monitor, analyze, and to act also on our water distribution systems. Which are the main components of this proof of concept? First of all, we have an hydraulic simulator that includes also a digital twin. And this hydraulic simulator is based on Eclipse Ditto, that is a framework to digitalize and implement a digital twin of sensors. This is integrated into a simulator that is well known in the framework of the water distribution systems, that is named EPANET. And on top of this EPANET, we combine also water network tool for resiliencies. That is another simulation that dynamically has been adapted by our group in order to interact and to implement this digital representation. Then we have an IoT network. This IoT network is based on LoRaWAN and includes gateways, servers, and also, obviously, the cloud where the implementations of our applications run. And in this cloud, we include machine learning-based algorithms, and specifically we have algorithms based on graph neural networks and deep neural networks that are used, we will see in a while, for prediction, anomaly detection, and demand forecasting. Going more into detail, into our Splash implementation, we have a real IoT network that is the input of our digital twin. The digital twin is synchronized, as we have observed this morning by Fabrizio Granelli. We need the synchronization of the data from the real network to the digital twin. On top of this, we are able to run our hydraulic simulations and to implement our machine learning algorithms. The final goal, as said before, is that the end users that are, for instance, water municipalities, water operators, are able to act on this platform in order to control, visualize, manage, and in case, as said before, to act on this. As for the proof of concept, this is the first real implementation that we have developed, but our goal is to continue till the end of the project to have other implementations. So this first implementation is in a specific deployment site that is a location in the Sabina area in Lazio region, and the city is named Castel Sant'Angelo. There we have a real municipal water distribution network, and we have two operators that are working in the project. One of these is the IoT operator, that is Unidata SPA, which provides the connectivity thanks to their water meters. And then there is Acqua Pubblica Sabina, that is the water utility company involved in this region. How this region is done? We have a region that is, generally speaking, of about 2,000 square kilometers. In these 2,000 square kilometers, we focused on a specific area. In these 2,000 square kilometers, there are about 4,000 water meters managed by Unidata. 70 of these water meters are integrated into Splash. The data have been collected in the recent months, starting from January 2025.
So basically, the Splash interface is divided into 4 main tabs. There is the home page, which is used for data initialization, both in terms of historical database and in terms of real-time data for the simulation stream. And there are 3 main applications: the map framework, the time series visualizator, and the network simulator. Moving into more details, the mapping physical framework is used for mapping the whole IoT network. In this example is the Castel Sant'Angelo area. All the devices are provided by Unidata, and we have 2 main views. We have a gateway-centric view, which allows us to point at a single gateway and map on the map every device, which in our case are smart water meters, that communicated with that gateway in that specific period of time. We can do it also the other way around, so we can select a single device, which is a smart sensor, and visualize every gateway that that device has used to communicate with the network server. Moving on to the time series application framework, here we have, in some way, a similar view. So we can have an aggregated view of the whole network, meaning we have the water consumption in terms of liters per hour of the whole district of Castel Sant'Angelo, and it is very useful to detect anomalies or hidden leaks throughout the water network. Or we can inspect the single behavior of a single smart meter inside a house to detect like unusual patterns or anomalies. The final tab is the simulation framework. Here we are merging the real data coming from the database with the simulation data. And we can use this framework to inspect if the real data is corresponding to what we expect to be the normal behavior of the whole network. You can inspect either the real-time statistics for the aggregated demand of the network, but also inspect the single nodes and see the pressure, the demand of a single sensor simulated inside the network. The user can interact directly with this user interface, launch the simulation, stop it, and also inspect every single item that is currently mapped inside the network. So right now, I'm going to switch to the terminal. Can you hear me? Okay. So this is the home page. We can select a city of we want to inspect. In our case, there is Castel Sant'Angelo. Here there is the data range we want to inspect. I'm going to leave it to default for this demo. We can confirm the database for historical data, but also for this demo, we want to initialize the real-time data stream for the simulation. First thing first, we can move to the mapping framework. Here we can inspect all the gateways that are currently deployed in the Sabina region by Unidata, which are more than 200 gateways. And as I said before, we can go to the gateway view and selecting from a huge list of gateways, which is indexed by number of transmission in that period of time, we can select a type of signal quality of the network we want to analyze, such as SNR or RSSI, and show or map every device, which I remember are smart water sensors that have communicated with that gateway. For each device, we can inspect both the number of transmission that it has had with that gateway, but also the radio quality signal. For our demo, we are gonna analyze more particularly this district called Paterno, which we have currently deployed in the water simulator. Finally, in the mapping framework, we have also the view the other way around, so we can select a single device and inspect all the gateways that that device has used to communicate with the network server, like in this case. Moving on to the time series tab, here we can do, as I said, a similar thing, so inspect the network from an aggregated point of view, or from a more precise single device point of view. So in this case, I'm going to select by default this device. I'm going to select, for example, the whole month of May. And I'm going to update the time series. And you can clearly see the water consumption of this single smart meter. We have the classical consumption of an high peak early in the morning, corresponding usually to the breakfast time, and also 2 other peaks in the lunch and the dinner. The same thing can be done in an aggregated point of view, so we can see the whole time series of the aggregated city of Castel Sant'Angelo. Moving on to the final tab, here there is the simulation tab. The user can interact, as I said, with the whole simulation. This is the Paterno district of Castel Sant'Angelo, as I said to you before. I'm gonna now launch the simulation, so it starts updating the values. On the right-hand side, there are some general graph statistics like the number of junctions, tanks, and pipes throughout the network. Down there is the simulated demand for the aggregated network and the real-time demand coming from our database. This keeps evolving throughout the simulation. And inspecting a single node, there are many properties of the node we can inspect, like the node identificator, which are the same one covering from the real deployment, and also demand, pressure, and position. So this is the node 2342, and for this node, if we wait just a couple of seconds, you will see the simulation data coming from our simulator and the real-time data coming from the database data. So now I'm going to stop the simulation. I'm going to go back to the presentation. Right. Here I have prepared you just a slide. We waited a couple of minutes and see both time series converging to the same values, both for the simulated demand and for the real-time demand.
Okay, thank you, Marco. And so this is the starting point of our project because now the platform is fully deployed. And on top of this, we aim to include other components that have been already designed in our project. Specifically, starting from the left side, we have already designed the algorithms for the data reduction and reconstruction. The goal is to use as less as possible data from our networks, because as you have seen from this picture, for instance, we have in a very small district about 400 junctions. So if we scale to larger networks, it's very complicated to include all the data that are collected there. So we are going to implement algorithms that are able to reconstruct our water flow signal from less data that are collected on the network. After this, we will be able to implement also time series prediction, that is to predict the future, even if Roberto is not so happy to predict something that will happen later, but this is very useful instead in the water demand sector, because operators, they would like to see what is going to happen in order to better optimize their resources there. Then we are also able, thanks to machine learning approaches, to detect anomalies in the network, that is, for instance, water leakages and other kind of anomalies that can happen on a water network. We are also able to classify the kind of meters that are collecting data in a specific time moment, and this is another requirement that comes from the water network operators. And finally, we aim at including the possibility to select and to include into the platform smart contracts in order to give to the final users the possibility to select their better tariff and pattern in order to use in a quite optimized way our water network infrastructure. As I said before, I would like to stress again, all these modules have been already designed into the project, So the next 6 months is the final step to include them into the platform that you have observed now is already operating. So thanks for this. This is Splash, and I think that is exactly what we need right now.
Thank you, Francesca and Marco. Any question from the audience? Oh, I just have a comment / a question.
Yes.
I guess you could easily use this also for other facilities, say gas distribution or something, because in that case, maybe it's also nice to study correlations or to predict issues or anomalies from one sector to the other, because there are a number of studies that they are correlated. Have you thought about, say, try to sell it for gas distribution, for example?
Yes, thanks for the question. Yes, we are quite confident that this kind of framework can be used also in other contexts, and where maybe there are topics that are important to be observed with this kind of instrument. For sure, the energy sector, where already we know there are a lot of studies and results as for the forecasting, the energy management, but also in other contexts. For instance, recently we had the occasion to speak in the framework of the smart agriculture, and also there they are very interested in this kind of framework that includes the digital twin of the infrastructure that you would like to observe, and the possibility to use it digitally in order to have this kind of prediction and other stuff.
Okay, so thanks again to both of you. Okay, so the next speaker of the session is Stefano Giordano from the University of Pisa.
Hello, everyone. The title of my presentation is On-Field Wildlife Monitoring. The Watch Edge action in support of the integration of computing and communication in rural areas. The name of Watch Edge stands for Wide Area Agile and Flying Network Architecture for AI Surveillance Processing at the Edge. Is a focus project within the Spoke 8 intelligent and autonomous system of Restart. And you see, Watch Edge studies an advanced edge computing and networking architecture distributed across several geographically distant sites to support environmental surveillance applications that make a use of extensive use of AI. And it is coordinated by Politecnico of Torino, Professor Guido Maier, and sees the participation of University of Catania, University of Pisa, and University Milano Bicocca, together with the Center of CNIT RAS, and 3 companies, Italtel, Nextworks, and Sensor ID. Here we are speaking about a real problem. We want to fill the gap between technologies and the real needs. And our needs is related to the presence of wildlife in our territories. You see here the level of the presence of these animals in Europe and what happens in some regions such as my one, Tuscany. It is a terrible problem where 45 persons per year that are deaths for accident on roads due to the crash with those animals. And there are estimated 60 million euros of damages in valuable crops in the agricultural losses. There are also very terrible problems related to infectious diseases such as African swine fever and there is a terrible impact on biodiversity. Unfortunately, you see, it's very difficult to have correct estimates of this situation awareness in our territories. Some of the data are old, more than 15 years. And there are only two possibilities. Or you transfer, you capture the animals, or you kill them. And you can easily understand that is something that involves people from the environmental sector, ambientalists, public administration, decision maker, hunters, and of course, farmer and agricultural companies that are terribly angry about this problem. You see here about the capture. You can imagine the fighting among the different sectors, and of course, the traditional way is to involve volunteers, dozens of non-experts that are recruited a few times per year to try to analyze. They obtain some piece of paper, such as that one, where you have to recognize male, female type of animals. And you can also use trap cameras, such as the trail camera shown in the lower part of the slide. But you notice you need volunteers, typically PhD students from the biology sector, that every 2 weeks go there, change the battery, take the SD card, etc. So we want to propose a digital transformation to this traditional approach. And this was done by Watch Edge, that proposed the island concept. This is the center of the talk, that is defining the function that are present within each of the territories that are totally autonomous and want to exploit edge computing. You see, we know very well that cloud can be provided on large container. We want to provide cloud in a trolley. We want to provide edge computing, very easy to deploy edge computing solution, such as the one that Italtel is proposing within the project. And also 5G. We have a trolley with 5G in a box that is present in one of these islands. The island that I will present is the one under the responsibility of the University of Pisa, that has this edge, far edge, extreme edge, and cloud in the backstage situation, a cloud continuum where even our data center, the green data center of University of Pisa, is within the park, okay? So we have all the cloud continuum toward the edge devices. And this island was chosen in a place in the park that is called Pineta. Of course, you see there other islands, Piaggerta and Boschetto, that were under the responsibility of Politecnico Milan, University of Catania, and all the other partners that are working within the Watch Edge project. So, first of all, someone can think that introducing artificial intelligence is collecting some image, then doing some processing, and put, some neural network in hardware-accelerated device within our cameras. On the contrary, it's a terrible task where, first of all, you need to build up good data set that are in some way certified by experts. You see the larger data set worldwide on wildlife, the Serengeti data set, that is totally unbalanced, is a typical case of citizen science where everyone can give some more picture of an animal, but you don't have any certification for expert. And of course, the data set is totally unbalanced. On the contrary, in our work, we realized our data set. We had experts deciding the type of animal and labeling the type of animal that we set. And then we train our neural network with a balanced data set with independent images. Of course, there was later on the issue of the choice of the neural network. So we compare several neural networks, we choose the best one, and then we try to squeeze some of these neural networks within the devices that are hardware accelerated. So offline, we do the training, and we do the inference online of our smart cameras. This is the island under the responsibility of University of Pisa. There is a Starlink satellite that gives the communication in the middle of nowhere, where there is no 4G, no 5G connectivity coverage from our carriers, licensed carriers, but they didn't give us the possibility to switch on our 5G in a box, private 5G solutions. We have the SIM, we are ready, but we had no any cooperation with them. And of course, this should be one of the cases where you provide the platform, not only for the surveillance, not only for the classification of animals, but also for other cases, such as the detection of fires or the analysis of the health of the trees in that territories. I think that is very, very relevant to push in that direction, avoiding the use of totally useless frequency band, such as is the case now in Italy. Nevertheless, we have a point-to-point link that substitutes 5G in our case, that reach a smart gateway that is powered by solar panel, so we have energy harvesting there, and from there we are using Halo 802.11ah to try some solution at 868 megahertz that give us more possibility of coverage in this rural area where, for instance, LoRaWAN was absolutely not able to function. So there is here 3 different types of wireless technologies: Hello, the point-to-point link, the satellite networks, and we are ready also to use 5G. You noticed for the connectivity of our edge device, we have the possibility to use the region Tuscany network and also commercial 5G there, since a little of coverage for 5G at the level of that building is possible. So we are building up our prototype camera. You see on the top the possibility of connecting it to the 5G router, also trying RedCap. We are ready to try also RedCap in that case. We are using Halo, as I mentioned. There are a lot of devices. I like the issue of actuators. We need the light during the night to see the scene, and these infrared LEDs that are lamps in the case are lighting at 940 nanometers region where the wolf and the deer are not able to see that signal. And then you see all we need for the solar panel regulation, MPPT control, the batteries, and also some filters that can be used for the night vision, daylight vision of the cameras. Of course, there is within the smart wildcam a logic to decide when it's necessary to start the acquisition of a new image. And of course, everything is programmable there, and we can compare alternative solution. We move the images to the edge, to our central server, where 2 databases are running, one for the data, and it's a time series database, and the other one is an SQL database where there is collecting the images. Here is the situation. You see the Starlink connectivity, you see the point-to-point link, the Lamayalaya swine-born that we are using, where again there is a solar panel for the smart gateway, can be also equipped with other type of hardware accelerated devices, such as Raspberry that we are using in that case, and then the smart cameras that you see on field. And our idea is to collect at least some heat maps. We are providing this idea, we proposed this idea of heat maps, okay, counting in certain territory how many times you see one of the 5 different animals that we classify. But we also proposed to correlate our acquisition with the time of the day and with the temperature. And you will see in our dashboard how relevant is the issue of temperature. We are measuring temperature and humidity in our smart camera. And you see, this is the dashboard. We are counting the animals. We see the animal in the picture. We can control the temperature. We can control any possible details on the functioning of this system, the platform that we are proposing. You see the humidity and the temperature that we want to correlate with the behavior of the animal. For us, it's very interesting also to control the allocation of resources, GPU use, CPU use, and of course, the radio links, and how this static solution that we are proposing can be adaptive in some cases. For instance, going to a lower consumption state where the batteries are in a critical condition for the energy consumption. So you see that we are controlling all the harvesting from the sun and in the different devices, the cameras, the smart gateways. The edge is powered by the grid. So also the allow for us, it's one of the parts that we are monitoring in the performances, and you see at a certain lower speed, under 1 megabit per second, until also we measure around 4 megabit the peak rate, that for us is something feasible. Now I will move to the demo, so I will connect to the other PC, where I try to move it here, where you see, first of all, the asset management. If you have many of those devices on field, it's very relevant to know which is the software that you are using inside, which is the version, which is the battery, the solar panel, the type of asset that you are using. And now we have 2 cameras, 1 gateway, and the edge. I want to try to connect here. You see that, for instance, about the temperature, we have 3 types of temperature. We have the temperature of the onboard devices, the GPU and CPU temperature. You notice around 60 degrees. We have the box temperature, 42.9 degrees now. We have the environmental temperature outside. So we are taking account also all these type of measurement for our knowledge extraction to try to collect some information correlated to the animal behavior. Then we have the analysis of the power. You see here all the level that we obtain from this from the consumption of the devices. Usually, yes, in this idea of semantic communication, we are borrowing computing with the telecommunication, and of course, computing is consuming much more than the transfer of information that you can see here too. So we have all the analysis of the current, the level of the voltage, and the different measurement that we are collecting there. Of course, the most interesting part is related to the analysis of the resources that we have here, and I want to kindly ask my colleagues on field to present the movement of the synthetic wild boar, since of course we cannot have wild boar with this temperature outside. So I would like to ask my colleagues that are following directly there if we can have, you see, they move the wild boar and there is a detection with 86% that this is a wild boar, and this is done by our smart cameras on field. I think that also we could see them. Those are the images collected live during the demo. The satellite is working. I can tell you a lot about the satellite. We are using the professional dish, but I think that this demonstrated what we have done and all the aspects that can give the possibility to extract knowledge for the network orchestrator and to react on the functioning on the network. I want to conclude my presentation, if we can come back to the presentation, to my presentation, only saying that, of course, and now we are very happy about the idea of having distributed artificial intelligence on field, not such as within a data center with 800 gigabit connection, but with very bad wireless connectivity. But nevertheless, we are studying this idea of AI splitting, or neural network splitting, distributed artificial intelligence. That is our main task, to demonstrate the integration of communication and computing. Thank you very much for your kind attention.
Thank you, Stefano. We are a little bit behind the schedule, but if there is a quick question from the audience. Okay.
Yeah, thank you very much. I was wondering about the scalability, and in particular, I have in mind the application of this to the monitoring of predators like the wolf, which has also a large impact on farmers and breeders. Yeah, I would like your comment on that, because with the wolf you have very fewer animals, and maybe on a larger area, so you have to spend more to find maybe a single animal. Yeah, that's what's my question.
Okay, I will give you the example of my park. In my park, there are around 11 wolves that are monitored. They have collars. 4 of them have collars. They are here now. In 2 hours, they are on the Vesuvio. In 2 hours, they come back here. So they have extreme mobility. And in this case, this possibility of detection is something that is in some way in support of analysis that have to be conducted with our other tools. Nevertheless, for the scalability, the basic idea is to have cluster of cameras in every island. And as I told you, the different islands are totally autonomous. But at the higher level of the data center, you can have federated approach. Federated learning, of course, but also some other federated correlation that can help also in this domain of the wolf analysis. Thank you for your interesting question.
Okay, thank you. Thanks a lot, Stefano. Okay, so the next talk will be given by Roberto Pecuri from Politecnico di Milano.
Okay, good morning, everyone. Oh, can we go back to the presentation? La presentazione, sì. Okay, good morning, everyone. So, during the last plenary, we presented the integration of a deterministic channel model into a network simulator. More specifically, we presented the integration of NVIDIA Shona, which is an open source ray tracer, into NS3. And we also demonstrated the impact of this integration on the application layer performances. More specifically, of using a stochastic instead of a deterministic channel model, or also combine them if it is the case. This tool actually enables us to simulate complex and dynamic networks. And I think a good example of them is vehicular communications, or vehicular networks. Today, I will present to you the evolution of this work, which is called VaniTwin. VaniTwin is an accurate V2X simulator with a ray tracer in the loop, of course. So it takes as input the digital twin of the propagation scenario, as well as the digital twin of the cars moving around these scenarios. It is a full stack tool. It is multi-stack, so it supports different technologies, and it also supports the simulation of multiple technologies sharing the same spectrum portion, which is a very interesting topic because eventually multiple vehicular communication technology will coexist on the road. As far as mobility is concerned, Vanetwin actually supports the simulation of mobility using Sumo or Carla, which is based on Unreal Engine, very common tool for computer vision studies, as well as real GPS coordinates, so as well as pre-recorded ones or live from the physical world. So, like in this example, we will actually study it later during the live part. We have two cars, a receiver and a transmitter, that are on a line of sight state. And then there is this truck that interrupts the line of sight. So thanks to Vanetwin and the fact that Vanetwin is a full stack tool, we can extract the KPIs of the network and analyze how they vary in these situations. Of course, the theme of this demo is actually this question about how do V2X digital twins, how are they able to enable safer streets? Well, I think it's best if we proceed the step-by-step. V2X communication do enable safer streets. This is a very interesting study conducted in Germany. They took 925 car accidents that really happened, and they found out that if autonomous emergency braking systems are activated by V2X inputs as well as onboard sensors, actually we have an 82% reduction. With onboard sensors alone, this reduction is way lower, around 52%, according to their data. When we talk about V2X communication, it actually varies the content. It can be information about the state of the cars, so speed, heading, position, as well as more complex data. An example is sensor data. So if we are able to get sensor from a neighbor car, we can then merge and extend our vision. Sorry. Digital twins can be very useful tools for this purpose, because we can exploit their capability to predict the future, so predict future KPIs. So if we are able to know that the throughput, for example, will drop, or if we have higher losses or the latency will increase, then we can use these KPIs as an input of a decisioning algorithm. For example, in this case, a decisioning algorithm handling the sensor sharing. So then we can take more informed decision about, for example, change the communication parameters in order to make the communication more robust, or send only partial sensor data, or lower the quality of a camera, for example. I think it's best if we go live now and see Vanetwin in action. Possiamo cambiare sul mio PC? Grazie. Does this work? Yes. Nice. Let's start by having a look at the digital environment. As I told you, Vanetwin takes as input the 3D digital twin of the propagation environment. Oops. Here it is. As you can see, for our example, we have all the buildings modeled with quite high definition. We will see, this is the road that you saw in the video before. And of course, we also have the cars, as I told you. The cars are currently parked here. And also the cars are modeled with high definition. And we can, of course, also increase the precision of this definition by saying that each component of the car has a different material, so that when the electromagnetic wave interacts with the surface, it behaves in a different way. I'm actually right now connected to a server in Milano. This server specifically handles the part about the propagation, so it is the ray tracing component. It's running on a server with GPUs, but Shona, even if Shona is a tool by NVIDIA, actually can run quite well also using CPU alone. I want to underline that. I think it's important. This script, of course, handles the computation of the rays and the extraction of the channel parameters that are then sent to the network simulator, which is run on this server. This is an NS3 simulation, very normal NS3 simulation. Here we define the communication stack, the details about the mobility, all the KPIs that I want to extract from the application level, so that I can then feed them whenever I want, which is the good part of a digital twin. Here I am modeling the transmission that I showed you in the video of the front car sending data to the back car. And I am using for this demo pre-recorded GPS traces for the vehicles that were pre-recorded on the road. I think we can run the simulation right now. Okay, everything is going well. Nice. And we created this dashboard to show you what can we export from VaneTwin. For example, here I'm showing the RSSI of the received packets, as well as the SNR, and the average latency of the communication, the throughputs, and the loss rate. Here, you can see a map of the scenario, which is changing. You can see that the truck now interrupts the non-line of sight. We have retransmissions, the latency goes up, and all of these are very useful information to be fed into a decisioning system. I want to show you a quick bonus point before going to the questions, which is, of course, to demonstrate you that the vehicles are moving in the scenario. We have mounted on top of them antennas, and we compute the propagation rates between them and extract the channel parameters. This is the same scenario. As you can see, the cars moved, and they almost reached the end of the, the simulation. That's pretty much it.
Thank you, Roberto. Any question?
Thank you very much. I was wondering whether you have looked into how much of a difference a better accuracy in modeling and simulating, let's say, in a more accurate digital twin makes to the decisions that you have to make, or how much that influence the figure that you mentioned at the beginning, so this 30% of collisions that you can avoid. Thank you.
Well, we are conducting studies for this point of view. Of course, having more information fed into decisioning algorithm, then the decision will likely be more accurate. Right now, studies conducting for this purpose use a probabilistic approach. They actually roll a dice and say, okay, the communication works fine. No, it does not work at all. But it's not always black and white. So this could really help, and also to develop some mechanism for sensor sharing handling that are more accurate and closer to real life.
Any other question? Okay, so thanks, Roberto, again for your presentation. So the last talk for today is going to be given by Giovanni Perin from the University of Brescia.
So thank you, Michela, for your introduction. Today, I will be doing my first presentation as an affiliate of the University of Brescia. And in particular, I will present private sensing via beamforming with commercial Wi-Fi devices. So, as we know, so the key features of 6G networks are mainly two. The first one is the presence of pervasive artificial intelligence and distributed across the network. And the second feature is integrated sensing and communication capabilities, which is what this presentation is about. In particular, we are considering Wi-Fi commercial devices. We have a transmitter and a receiver, and integrating sensing and communication is trying to communicate while also understanding what is in the environment between the transmitter and the receiver. We are considering a setting where there is also an attacker who is trying to opportunistically use the signal from our transmitter to try to infer what is in the environment between our transmitter and themselves. What we want to do is prevent the attacker from doing this free rider attack, and also allow our legitimate receiver to instead doing sensing. More specifically, this is the setting. We are considering a MIMO setting, so we have more than one antenna from the transmitter and the receiver, and also we are considering multiple antennas for the attacker. This picture is our laboratory at the University of Brescia. We can see the transmitter with 4 antennas that is transmitting to the receiver, which is on the other side of the laboratory, and it has 2 antennas. In this first video, we can see a normal day with people working in the lab. And you should have seen also the transmitter and the receiver. We need just a little background, but I promise there will not be a lot of math. So when we perform a transmission, we go through a channel, and the channel is denoted by the matrix H. We can perform a singular value decomposition of the matrix H, and in particular, we are interested in the 2 matrices that you see on the right, which are sigma and V. Sigma is a diagonal matrix with eigenvalues or singular values, because they might be also zeros. And V is the matrix of the right eigenvectors. Usually, what is done in Wi-Fi, and in particular in beamforming, is that the transmitter does not transmit really the signal we are interested in, but it adds a precoding matrix, and this is done to facilitate the receiver in retrieving the signal, because it's like a pre-inversion of the channel. So the actual signal that is transmitted is X prime, which is the multiplication between this precoding matrix W and the actual signal. It is proved that the optimal precoding matrix is the one having the first right eigenvector of the matrix V. So at the end, what we are transmitting is the multiplication between V1 and X. So now let's imagine that we are at the attacker, and what we see is another received signal that I called Y tilde, that is the product between H tilde, the channel of the attacker, and the actual signal transmitted, so V1X. This Y tilde is a fingerprint of the environment, and we want to hide this information from the attacker. In particular, what we could imagine to do is to try to multiply V1X by a random coefficient that we call M1, that is only known to the legitimate transmitter and receiver. This random coefficient changes during time, so that the environment, the fingerprint, is obfuscated at the attacker. Unfortunately, if the attacker has at least 2 receiving antennas, which is the assumption of a MIMO system, this doesn't work. Because the attacker, what can do is dividing the signal that is received by the 2 antennas, and the contribution of the random coefficients will be deleted. At the end, using the ratio between the 2 signals received at the 2 antennas, there will be still the fingerprint of the environment. So what can we do to overcome this issue? Is instead of only using the first eigenvector of the precoding matrix, use all of them. And this is the solution. If we try to put some weight to all of the eigenvectors, at the end what happens is that by using the ratio, the coefficients do not delete anymore. This is the idea behind what we were doing, and now we have some videos showcasing this. So here we have the environment that is empty, and at a certain point there will be someone that is a PhD student from the University of Brescia, Giovanni, that is moving, and we can see that the clear CSI and the deobfuscated one that is following the clear signal is different from the obfuscated signal. Maybe this will be more evident in this video that shows the laboratory which is completely empty, and indeed the CSI, the clear CSI, which is the one in red, is static. The obfuscated CSI, which is the one received by the legitimate receiver, is more or less following the clear CSI, and we see that instead the obfuscated signal varies during time, and the attacker doesn't know if this is true because someone is moving in the environment or because we are changing the environment fictitiously. This is the waterfall of what we have just seen. So in the figure on the top, we can see the clear CSI across time that is static because the environment was static. And the obfuscated CSI is what the attacker sees. And as you can see, there is a lot of noise, and it's impossible to understand whether something is happening in the environment or not. Unfortunately, as we know, there is never free lunch. So what are we losing? What are we losing is SNR in communications. So if we take the expectation of the power of the received signal over the one of the transmitted signal, what we end up in having is a formula that depends on the coefficients that we have just introduced. And in particular, if we maximize the SNR, we see that we retrieve the optimal beamforming, and that was why that was optimal. We should give all the mass to the M coefficients to the highest, to the strongest eigenvalue. So if we use our approach, what happens is that the SNR lowers. We have also another experiment where Giovanni moved from one position to another on a checkerboard in the laboratory. And we tried to perform a localization task where we trained a neural network to localize Giovanni in the clear space. What happens is that if we test with clear data, of course it works well. It also works well at the legitimate receiver by deobfuscating. And of course, if we instead try to be at the attacker with the same neural network, we are not able to localize the position of Giovanni. There is a small caveat, which is the position number 2. The problem there is that Giovanni was in line of sight. So at the end, of course, the received power is a lot less, and the attacker can understand whether Giovanni is in line of sight or not, even if the signal is obfuscated. So to conclude, what we have done is that we have developed and showcased in a demo a method to prevent unauthorized sensing on Wi-Fi commercial devices while still allowing it if the user is legitimate. And we have found out that we have communication and privacy trade-offs. Particularly if we use optimal beamforming, the communication is good. We have the best SNR possible, and we can perform sensing if we are at the legitimate receiver, of course, because the signal is clear, but we have no privacy because the signal is clear also for the attacker. If instead we try for an intermediate approach, the SNR will be medium, privacy will still be medium, but the obfuscation will be unstable because sometimes we cannot invert matrices at the receiver. If instead we use orthogonal coefficients, we will have the possibility of having a very good deobfuscation because the system of equations is perfectly invertible, and we have also perfect privacy. But as I showed you in the previous slides, the SNR will be low, and we are losing in communication. So that's it from my side, and if you have any questions, feel free to ask.
Thank you, Giovanni. Any question? I just have a quick one. Maybe you mentioned it at some point, but of course you need the transmitter and the receiver to exchange some signaling, some information about how they do the random
Yes,
coefficient,
correct.
right?
This is done in channel sounding moments that happen every 10 milliseconds.
Okay.
And currently the standard says that this channel sounding is done in a clear way. So this is a problem because the attacker will read in the channel sounding moments and can sense during channel sounding. This procedure can basically we should modify the standard in order to do channel sounding with the previous random coefficients so that only the transmitter and the receiver know the code of the new channel sounding.
Okay, yeah. Any other question, comments? Okay, so thanks, Giovanni, and all the other speakers again.
Thank you.
Thank you, Michela. So now we have the slot dedicated to the demos of the project, so you can go and visit the booths. So again, go there. There will be new demos and activities presented there with respect to those that you've seen yesterday. I just want to remind you that there is a QR code on each of the demo tables where you can vote your preferred demos. So there will be an awarding at the end of the day today, and I recommend you to come back here at 2:30 sharp because we will have another interesting set of presentations. Thank you.